About chapter 22. We're going to do problem 13 and problem 17, and then we're going to do 55 in quotation marks. We're not actually going to do it. I'm going to give you some strategies, some hints. So number 13, we have a charged particle that's moving in a circle inside of a magnetic field. They tell us it's a proton. So we have a proton that's moving into magnetic field, and it's moving at a velocity of 7.5 times 10 to the 7 meters per second. The radius of its path is 0.800 meters. And we are asked to find what's the magnetic field that this thing is moving inside of. So what is B? How do I find B if I know the radius of B?
MV over QR.
MV over Q R? Where did we get that from? I don't remember that equation in the book. What equation do they give you in the book? R is MV over QB. So I multiply the B to the other side and divide by R. So I get B equals MV over QB, QR. Yeah. Do I know all these? Do I know the mass? What kind of particle is it? Proton. Can I find the mass of a proton? Yes. Coincidentally, if you ask Google what is the mass of a proton, it will tell you I don't know. You have to actually type in and Google it. You can't ask. It's tests. What's the mass of a proton? Yeah, but Google should know that, and it doesn't. It's useless. Yeah, it's on your cheat sheet. 1.67 times 10 to the negative 27. So after this, you just plug and chug your numbers in. 1.67 times 10 to the negative 27 times V, which is 7.5 times 10 to the 7, divided by Q. Oh, what's Q? 1.6 times 10 to the negative 19. I thought that was an electron. They're the same. B equals, you don't have to say it like I'm an idiot. So you plug in all these numbers, and what do you get for B? Some of you would not make good teachers. Your students would cry every day. They're the same. I know that. Somebody type it in the calculator. Let me know what it is.
0.979 Tesla.
979 Tesla. We'll assume Mark is right. Otherwise, he'll shock me with his shocking tool. Hook me up to the patches. Okay, any questions on number 13? No? We're good on 13. Wonderful. How about number 17? Let's do number 17. And number 17, we're given something called a velocity selector. I'm going to draw a picture and show you what a velocity selector actually is after we do this problem. But there's an equation that's particularly relevant for a velocity selector. What equation is relevant for velocity selectors? V equals E over B. And what is the purpose of a velocity selector? What does it let you do? Say it like I'm an idiot. Select velocities. That is the literal purpose of it. An electric field and a magnetic field, you can adjust the strengths, use whatever strength E and B you want, to get out whatever velocity you want for a particle. Okay? We are told we send a particle through with a velocity v equals 4 times 10 to the 6 meters per second. We are told that the magnetic field that we're sending this through is 0.10 Tesla. What is the electric field? How do I find the electric field then? From this. Is B times V. So I multiply both sides by B to get the B over to the left. Cancels on the right. E is B times V. So the electric field is 0.1 Tesla times 4 times 10 to the 6. Without even using a calculator, we can see that this is 4 times 10 to the 5th volts per meter. How do we get that without a calculator? Multiplying by 0.1, that means you move the times 10 to the 6 becomes times 10 to the 5th. Take away 1. Or type it into your calculator. Some of you dum-dums probably need to do that. Not us smart ones. Ah, shoot, I'm recording this. I forgot. Part B. Part B, we're asked to find what is the voltage that's created by this if the distance it moves is 0.1 meters. How do I find voltage from this? I have an electric field. I have a distance. How do I find voltage? Not divided. V equals E times D. V equals Ed. Ed used to be a TV show. Anybody ever seen the TV show Ed? I'm not talking Mr. Ed. That's the talking horse. Just plain old Ed. It is about a bowling alley lawyer. This guy that bought a bowling alley and he had a law degree. He practiced law at a bowling alley. It was kind of funny. V equals 4 times 10 to the 5th for my voltage, times my D, which is my separation, the distance I go, that's 0.1 meters. Multiply this. What do you got? 4 times 10 to the 4. Is it 0.01?
Is it?
Yeah, because it's 1 centimeter. So it's 4.01. So that'll be 4 times 10 to the 3rd. I retire from teaching. From now on, you will be taught by the twerking one. She will take over class. They're having fun over here. The right side of the class is having fun. The left side is not amused. They're laughing in their own little world. At me, not with me. Okay, so those are the problems that we're going to do today. That's all the problems we're going to do. 55, we're going to talk a little bit about it. We're not actually going to do it. What we want to do now is talk about velocity selectors and use that to understand the right-hand rule. So the right-hand rule lets us figure out directions for magnetic forces for charges moving inside of magnetic fields. It works very specifically. Let's say I have a charge. We're going to assume it's a positive charge. And I'm going to send it moving over to the right. And then I'm going to say I'm going to have a magnetic field. That's my velocity. I'm going to have a magnetic field going down. And I want to know what is the magnetic force that's going to act on this particle. Where is it going to go? The magnetic force. So the right-hand rule says you take your right hand, use your right hand, not your left hand. You take your fingers and you point them in whatever direction the velocity is going. So what direction do I point my fingers? To the right or to the left?
Right.
I point them to the right. My velocity is going to the right. Then I rotate my hand around so that when I bend my fingers, they bend in the direction of the magnetic field. No, don't go crazy and try to bend your fingers backwards. There's only one way your fingers bend. So you want to rotate your hand around so that your fingers can bend in the direction of the magnetic field. What direction do I want my fingers to bend? I want them to be pointing down when I bend them. So is my hand oriented correctly now? No, what do I have to do to my hand to get it? I have to flip it, I have to rotate it. So if I rotate it, now my fingers are pointing down. What direction is my thumb pointing? You have to make sure that you're in the same plane as this paper. So if you're staring at the screen trying to do it, like, maybe rotate your chair so that you're looking directly at it. That will help. So I point my finger, I rotate my arm so that my fingers can bend down, and my thumb, where's my thumb pointing? My thumb is pointing away from me. It's pointing into the board. That's the direction of my magnetic force. Magnetic force is going into the board, and we denote that with a circle with the cross inside of it, with an X. We'll talk about away from the board too. Okay?
So that's in?
That's into the board. Yeah, we're going to do a few. Okay? The way you know that's into the board, anybody do archery? Anybody ever seen somebody else do archery? The Hunger Games? Yeah. You see an arrow, they have little feathers on the back, so this arrow is actually, you're safe because it's flying away from you. Yep. If it was coming towards me, out of the board, will be the point coming towards you. And then you run away, so you don't die. Let's do another example. Let's do V is going up. Let's do B is going this way. Okay, so what do I start with? First, I make sure I'm pointing at the paper. Fingers go up. What direction do my fingers need to bend? To the left. So I rotate my arm around so that my fingers can bend to the left. What direction is my thumb pointing?
Towards you.
My thumb is pointing out towards me. You hear that, YouTube? They all said, "Oh, I'm a great teacher." Let's do another one. Let's do V is going to the right. And let's do B is going out of the board. Okay, once again. You all get to see my bald spot. Fingers go to the right. What direction do I bend my fingers?
You don't know.
Not bending.
What direction do I need to bend them?
Away from the board.
I need to bend them away from the board. So right now I need to rotate my arm, don't I? And then if I bend my fingers, they're coming out. What direction is my thumb going?
Down.
Down. So magnetic force goes down.
Yeah, I'm confused with the last one.
Yeah, I thought the thumb was
Thumb is the force. We'll do it again. We'll get rid of that. And we'll do the exact same one. V. That's where your fingers go. They bend in the direction of B, and your thumb gives you the force.
So for this next test, are we literally all just going to be like going like this?
Oh yeah. Oh yeah. Except for there's going to be a couple of dumb ones that are going to be using their left hand. Okay. So what do I do? Where do my fingers go? To the right. Where do I need to bend my fingers?
towards.
I don't want to bend them towards me. If I do it right, my fingers are out. If I bend my fingers now, they're going into the board. I don't want that. So I got to flip my arm around 180 degrees, right? I flip them 180 degrees, right? Bend out towards me. Where does my thumb go?
Down.
Down. So the force goes down. Yeah. And some people do use their left hand. If All of this works for a positive charge. If you have a negative charge, use your left hand. Or use your right hand and then just flip the answer. I think that's easier. So let's try doing this with an electron. I trust you, you can do it. Where do you want, what velocity do you want? Where do you want the velocity to go? Up, down, left, right, in, out. Up. Velocity is going up. Where do you want the magnetic field to go? Up, down, left, right, in, out. Right. Okay. Where do my fingers go? Fingers go up. Where do my fingers need to bend? To the right. So I need to rotate my arm around so that they bend to the right. My fingers bend to the right. Where does my thumb go?
Away.
My thumb goes away into the board, but it's an electron, so I flip the direction so it comes out. Can I do it with if I do it with my left hand? Let's see. With my left hand, fingers up, bend my fingers, thumb's coming out. Right hand. Okay?
Yeah.
This is great for PT students because you'll need to do PT after you do these problems because you will contort yourselves. Okay? So let's see how this works in a velocity selector in an actual problem, potential problem. A velocity selector, I set up two parallel plates. I put positive charges up on one side, I put negative charges on the other side. That's going to create an electric field. Where does the electric field go? Towards the negative. So I'm going to create an electric field in between these plates that goes this way. Now I'm going to take a positive charge and I'm going to shoot it into this. Shoot it into here. Now let's imagine in a medical context, I'm trying to take some image and I'm taking an image by shooting charged particles at you, something like an X-ray or a PET scan, positron scan, literally shooting particles through your body. And I want to control where those particles go. To control that, I have an electric field here. Where's this charge going to go when I shoot it into here? It's going to go down. It's going to spiral downwards. So that means it just crashes into this plate, and if you're on the other side of this, it's not actually going to hit you and I'm not going to get my image. I want this to pass completely through. So to do that, I can set up a magnetic field in here that's it's called a crossed magnetic field. That means it's perpendicular to the electric field. And if I set it up correctly, then I can create an opposing force that will drag this up and it will just pass straight through. So right now, I've got an electric force that's pulling it down. That's the electric force. I got this guy. He's flying through. Electric force is going down. Here's my velocity. If I want him to pass straight through undeflected, where do I want the magnetic force to go? I want the magnetic force to go up, right? Okay. So I have a V going to the right. I have an FB that's going up. What direction do I need to set up my magnetic field? I have two choices. What are the two choices for where my magnetic field would go? I already have the right-left directions taken care of with the V. I have up-down taken care of with the FB. So what is that? What's the third directions that I have? I can be going in or out. So I can have a magnetic field going into the board or out of the board. Into the board or out of the board. Let's figure out which one of those is right. What direction do I want my thumb to point? I want my thumb is the force. So I want my thumb to end up pointing up. Yeah? So I can take my fingers, I put them in the direction of V. Yeah? If I bend my fingers into the board, what direction is my thumb pointing? Up. Is that what I want?
Yes.
Yeah. So is that direction I want? Is that the direction I want the magnetic force?
Yes.
Yeah. So I want to go into the board. So the question that we were asking is, what direction do I put my magnetic field so that this thing passes straight through? So that these forces balance. What if this was an electron? Opposite. I would come out of the board. Okay? And that's how we use the velocity selector. That's the right-hand rule. Did that help?
Yeah.
Hopefully. Yeah.
So
Abdul.
usually the velocity, the other stuff is given in the equation?
Yeah. Yeah.
Okay.
They'll usually give you 2 out of the 3. They'll give you a velocity direction, or electric field direction, or magnetic field direction, and you figure out the third. Any other preguntas? Your fingers are the velocity, the bend is the B, is the magnetic field, and then your thumb is the force. F sub B, the force due to the magnetic field you wanted to go. That's your thumb. Force in E is electric force. No right-hand rule there. That's where this charge goes because of the charges here. Why does the positive charge go down? It's being pulled. Why is it being pulled down though? Positive attracted to negative. Repelled by positive. Make sure you get this in mind and kind of practice this, because there's a second right-hand rule that'll come along that's a little bit different than this one. That's a next time we do chapter 22. We'll talk about the second right-hand rule. There's 2 of them. This one I always remember, fingers are V, bend is B, the magnetic field, and then thumb is F. Yep. Bend is B. Bend is the magnetic field. Okay, some hints I'm going to give you for 55, and then we'll give you the rest of the class time, about 20 minutes to work on problems, and I'll come around and help. So we have a picture that looks like this. We have some current going through this wire, and then we have a loop of wire underneath it with currents going around like this. Wire 1, wire 2, wire 3, wire 4. Good. I'm going to tell you something about magnetic forces, forces that act on current carrying wires. These wires, because there's current moving through them, are either going to be attracted to each other or they're going to be repelled by each other. This happens in wiring wherever you wire stuff. So either the wires move towards each other or away from each other. We can counteract this by putting plastic around the wires. So all the wires that you have plastic around, that plastic kind of insulates them so that they're not attracted. If we didn't have that, wires would cut and burn stuff down. So we don't want that. What they want us to do is calculate what is the force between these wires, and we want to know the magnitude and the direction. The magnitude is an equation, relatively easy to find that. The direction is a little trickier, so it will tell you if wires are parallel, then the following 2 rules hold. If the currents in the wires are in opposite directions, then the wires will attract each other. If the currents are in the same direction, then they'll repel each other. So let's see how that relates here. I have current I1. This upper wire, the current is going to the right, and this current, this wire 1, the current is going to the left. So, are these wires going to be attracted to each other, or are they going to be repelled by each other? They're going to be attracted. So this wire 1 is it going to move up, or is it going to move down? It's going to move up. So that is the direction for that wire. Second wire, are they moving the same direction or opposite directions? So wire 1 and wire segment 2, same direction. So are they going to be attracted or repelled? They're going to be repelled because they're going in the same direction. So this one's going to go down. For next class, see if you can figure out what happens with wire 3 and 4 and see if you can calculate the magnitudes. And then finish the rest of the homework problems. If you have questions between now and then, send them up on Canvas. Should all be working now. Yeah?